Sometimes when you're analyzing the motion of an object, you'd like to know what its acceleration, or you'd like to be able to analyze its acceleration in two different pieces. One part that changes the direction of travel of your motion, and the other part that changes the speed of travel of the motion. Before we can actually do this analysis, though, we need to know, well, what directions do show up in an acceleration. Now, one way to think about this would be to write down your acceleration function, but we can't say anything about r double prime in general, just starting with r double prime, because we don't know anything about r, so we can't say anything meaningful about r double prime. So another way to get at this is to think about, well, what is the change of the direction of travel? Remember that the direction of travel itself, we had a name for the unit vector in the direction of travel, and that was capital T. We called that the unit tangent vector. Capital T is 1 over magnitude of r prime times our scalar product with r prime. So what we could do is just write down the derivative of capital T and see what pops out. Okay, so let's work out this derivative. We're going to have to do a scalar product rule for this derivative. So first let's take the derivative of the 1 over magnitude of r prime part. So derivative of it's something to a minus first power. So when we take the derivative, do the power rule on the minus first power part, we get minus 1 times the magnitude of r prime squared. And now to do the chain rule, we have to multiply this by the derivative of the stuff in the denominator. And then we've worked this out before. The derivative of a magnitude, it's given by this formula here. So r double prime dot r prime over magnitude of r prime. Okay, so that's the derivative of just the 1 over magnitude. And now we have to do scalar product with r prime, so like this, plus, and now the other part of our scalar product rule, so leave the scalar part alone this time, 1 over magnitude of r prime, and then take the derivative of the vector part, and the derivative of r prime is r double prime. Okay, now remember what we were doing is trying to get a handle on what directions show up for an acceleration. Well, look, here's the acceleration. So what we could do is rearrange this equation to isolate r double prime. So let's do that. We'll move this first term to the left, and then we'll multiply both sides by r double prime. Or I'm sorry, multiply both sides by the magnitude of r prime. So when we do that, we get r double prime on the right-hand side, and on the left-hand side, we get a big mess. It's a big mess that's multiplied by the magnitude of r prime. So we get d capital T, d little t, plus, right, because it was minus, but we moved this term to the other side, 1 over, actually let me write this 1, so I'm going to collect up these scalar fraction parts. So the numerator is r double prime dot r prime, and then the denominator has 3 factors of this magnitude, so magnitude of r prime cubed times r prime. Okay, so what directions go into this r double prime? Well, one of these we can identify directly. So this one right here, this is a scalar multiple of r prime. So this is the tangent direction, right? So this is the direction of travel. In other words, it's the direction of r prime, or what amounts to the same thing, the direction of the unit tangent vector. Okay, so what about the first part here, d capital T, d little t? It seems like we might be stuck here because after all, if we don't know what the motion is, we can't really say anything sensible about its rate of change, d capital T, d little t. But actually, d capital T is always a unit vector, right? We've cooked up d capital T so that it's always a unit vector. And one thing we know about vector valued functions that have constant length is that for a vector valued function that has constant length, the vector valued function and its rate of change are always perpendicular. So this direction is perpendicular to capital T. And since it's perpendicular to capital T, it's also perpendicular to r prime. Okay, so whatever direction this points, it's actually a direction that's perpendicular to the direction of travel. So when we have an acceleration vector, which, right, of course, acceleration is r double prime, there is, sorry, I should draw a curve. So at this spot, there is the direction of travel, which is capital T, and the acceleration vector, it has a component parallel to capital T and a component perpendicular to capital T, right? So there's this other direction that is perpendicular to capital T, and we can get at that direction by taking the derivative of capital T. So that will tell us the other direction that makes up the acceleration. So these are the two directions we're talking about, right? The part of acceleration that changes the speed, that's in the direction of travel, and the part of acceleration that changes direction of travel, that's in this other direction. So let's name this other direction. We're going to call it, because it is always perpendicular to the direction of travel, we're going to call it the unit normal vector for the curve. Capital N is this letter that we're going to use for it. And just by definition, it is the derivative of capital T over the magnitude of the derivative of capital T. So, right, what this vector that we had up here, d capital T, d little t, it's in this perpendicular direction, but it might not be unit length. So we're making it, forcing it to be unit length here by dividing it by its own magnitude. So this is a unit vector perpendicular to our unit tangent vector, and the acceleration vector, which is r double prime, has a component in this direction. And the direction of t, right? So we've found, in general, you might expect the acceleration vector to have a component in the direction of t, a component in the direction of n, and a component in some third direction, but that's not the case. What makes this unit normal vector special is that the acceleration is in the direction of t and n. Well, the acceleration has a component in the direction of t and a component in the direction of n, and no third component. So that's what makes this normal vector special. Just to get a hang of this thing, let's actually calculate one. So let's find the unit tangent vector and the unit normal vector for this particular curve. This happens to be a helix. Because our sine and cosine are in the y and the z direction, and our x component is increasing linearly, this is a helix that's sort of wandering off to the right rather than one that's going upwards. Okay, so first we need to calculate capital T. To know capital T, we have to calculate r prime. So r prime is 2, comma, let's see, use the chain rule, 3 cosine 3t, comma, minus 3 sine 3t. Okay, so to get capital T, we also need the magnitude of r prime. So let's calculate the magnitude of this. So it's going to be the square root of 2 squared, which is 4, plus our y-coordinate squared, so 9 cosine squared 3t, plus our z-coordinate squared. Squaring gets rid of this minus sign, so let's not write down the minus sign. 9 sine squared 3t. So square root of all of that stuff. Now, it looks bad, but these two parts, right, these both have a 9, and when you factor out that 9, you get 9 times cosine squared 3t plus sine squared 3t. And, of course, cosine squared plus sine squared, because these inputs are the same, cosine squared plus sine squared is just 1, so this is 9. All right, so the upshot of this is that the magnitude of r prime is, let's see, 4 plus 9, so square root of 13. Okay, now we can write down our unit tangent. Our unit tangent vector is 1 over the magnitude of r prime times r prime. So this is 1 over square root of 13 times, and then r prime was 2, 3 cosine 3t, comma, minus 3 sine 3t. Okay. Next up, we need to calculate our unit normal. Remember, our unit normal is t prime over the magnitude of t prime. So let's calculate t prime. Fortunately, in general, calculating a unit normal is very annoying because, in general, this magnitude part in front of your, or this scalar part in front of your unit tangent vector in general is a function of t, and so when you take the derivative of this, you get some big mess. But fortunately, in this case, it's a constant, so we can just move the constant outside of our derivative and then differentiate this remaining vector part. So we get 0, comma, minus 9 sine 3t, comma, minus 9 cosine 3t. Okay. Now we can take the magnitude of this. I should note that t prime, it points in the same direction as n, right? Because t was unit length, t prime points perpendicular to t, and so it does point in the correct direction. It just isn't unit length typically, so we're going to have to divide t prime by its own magnitude just so that we get a normal vector that actually is unit length. So magnitude of t prime is, we can move this scalar multiple outside of our magnitude and then just calculate the magnitude of the vector part. So that's going to be 0 squared plus, let's see, 9 squared is 81, but I'm just going to write 9 squared sine squared 3t plus 9 squared cosine squared 3t. And then when we play the same factoring out trick, we can factor out the 9 squared. Sine squared plus cosine squared is 1, so we get the square root of 9 squared, so that's 9. So 9 over the square root of 13. Maybe it would have been more efficient to factor a 3 out at the very factor a 9 out here at the very beginning, because then the magnitude of the remaining vector part is just 1. But anyway, same thing. So now we have the magnitude of t prime. So now we can finally write down the unit normal vector. It is 1 over the magnitude of t prime, which we found to be 9 over the square root of 13, times t prime itself, which was 1 over root 13 times, I guess, let me factor out this 9 now. 9 over root 13 times 0, comma, minus sine 3t, comma, minus cosine 3t. And then when we simplify some stuff, notice that this actually cancels that. That doesn't always happen, but it did this time. So our unit normal vector is just this vector part here, 0, comma, minus sine 3t, comma, minus cosine 3t. Notice that this is unit length. If you compute the magnitude of this vector, if you compute the magnitude of this, you do get 1. And also notice that it is perpendicular to t. If we take our n vector and dot it with t, so t is hiding just off screen. Let me see if I can fit them both on screen at once. There. So, we get 2, if we dot t with n down here, we get 2 times 0, so that's 0, plus, so 3 over root 13, I need a plus here, 3 over root 13 times cosine 3t times minus sine 3t, So minus sine 3t plus, and then in my z coordinate I get minus 3 over root 13, so minus 3 over root 13, and then sine 3t minus cosine 3t. So I'm running out of room, so let me write minus 3 sine times, oh, I already picked up this minus sign. I moved it out front, right? So I already got that minus sign. So minus 3 sine times, and then there's a minus cosine. All right, and if you look at this, this one and this one, these are negatives of each other, so these add up to 0. So n dot t really is 0, and so n dot t really are perpendicular, and of course n is unit length because, well, look at it. You can use find the magnitude formula. So when we finally decompose accelerations in these two directions, one that changes the speed and one that changes the direction, the two directions we are talking about are t and n, the unit tangent and the unit normal.